last 15 questions. Part B, last 15 questions. But some of the questions relatively easy, so I skip. So the first two questions are pretty easy. Although small number of students missed the second one, yeah, but I will post my solution file after the class. So those students, they can study the solution files. All right, I want to spend my time mainly on the questions with more problems. The first one, number 13. Yeah. So this one, lot of problems. So let me explain. Yeah. First, the answer is 3 comparisons, not 2. Yeah. So many students give me 2 comparisons. Okay, all right. Answer. Because here we target the worst case. Yeah. So when you get 2 comparisons, you need to think about if it is the worst case. It could be the best case. Yeah. But that could happen, very common. Yeah. Many times students, I noticed the main problem, they didn't organize the data well. So they work on the data in some messy way. Then find one of the cases, it works, but that case is not the worst case. Yeah. That case could be the best case. Yeah. All right? Yeah. So let me explain the several problems in your solutions. All right. All right. So when we start, all right. So here we draw a diagram, try to get a visual understanding. Yeah. So here, the given condition, the known information, x3 higher than x2, then higher than x1. All right, yeah. Then, all right, so now, give you, some of the students did comparisons like this. First element, x to the 4th, do comparison with, let me see, yeah, x3, yeah, because there are different ways. Yeah. Then there are 2 cases, right? Higher, lower. Now, there are 2 cases, but you need to pick the worst case. Do not pick the best case. Okay, yeah, 2 cases. The best case is x4 greater than x4 here. x4 is greater than x3. Yeah. It's better. Yeah. But worst case is this. x4 lower than x3. Yeah. Yeah. Because if x4 is greater than, then you get a ordered partially ordered array with 4 elements. Only one last element left, x5. Then when you need to find the second one, yeah, even in this case, find second one. So that student compare x4 and x5. Then also best case, worst case, right? Also best case, worst. Then that student picked the best case. All right? Because, so that student, pick x5 higher than x4. Then you only need two comparisons, right? Yeah, but that's the best case. So if you pick x x5 lower than x4, then you cannot get the second largest, right? But still, you need to do more work. You need to do more work. Okay? Yeah. So here, because here, x3, if you compare x3 with x5, then x5 lower than x3 is the worst case. If x5 is higher than x3, then you get a solution, right? Yeah. Because if x5 is higher, also two cases. If x5 higher than x3, you already have the second largest, right? Yeah, two comparisons, you already have second largest. Yeah. So that's not the worst case, right? Yeah, that's the best case. So the worst case is you should get x3 is the highest. Then you have x4, you have x5. Both lower than x3. Then you need to do more work. Right? After you eliminate x3, then the candidates for second largest, there are three elements. These three elements all qualify for the candidates for the second largest. So you need to do another round comparison to find the largest in these three elements, two more comparison. So 2 plus 2, so in this way, because you have two comparison, right? Yeah. In the first round. Now, in this round, you need another 2. 2 plus 2. First round, second round. So you need 4 comparisons. That's not the best solution. Our best solution, 3 comparisons. Yeah. Now let me show you the best solution. Yeah. All right. Best solution, your first comparison, you compare x4 and x5. x4 and 5, that's your first comparison. Okay? Yeah. Yeah. We can assume x5 is higher than x4. So this is your first comparison, right? Yeah. All right. So now you have 3 ordered elements. All right. So second comparison between, so you compare x5 and x3. This is your second comparison. Yeah. So after second comparison, the larger one will be the maximum, right? Larger one will be the maximum. Okay? The smaller one will be the candidate of the second largest, right? Smaller one will be the candidate. Yeah. Yeah. All right. So the smaller one, there are 2 cases, x5 or x3, right? So the x3 or x5. 2 cases. If x3 is the smallest one, x3 is the candidate, another candidate is x4, right? So you need one more comparison, third comparison. Yeah. If x5 is the smaller one, then you need one more comparison between x5 and x2, also third comparison. See? Yeah. So in these 2 cases, you need 3 comparisons. So in this case, x3, so here, smaller, right? So here, we assume smaller. x3 smaller, then you need to compare x3, x4. If x5 smaller, you need to compare x2 and x5. The larger one will be the second largest, the larger, okay? So these 2, larger one equals second largest. So that's this solution. Yeah. That's this solution. Okay, all right. So here you can see from this question, yeah, when you do comparisons, you need to pick the worst case, not the best case. Yeah. Two cases. So which one will make the situation harder? Then you pick that. Not easier. Don't pick the case you need to do less work. That won't be the worst case. So you need to pick the case you need to do more work. Yeah. Yeah, here. Yeah, so we'll do that. But another important step is the first comparison should be between x4 and x5. If you do first comparison with one of the elements in this three-element ordered chain, then you can see you will need one more comparison. Yeah. Yeah. So here, I want to summarize a little bit. Yeah. Because later we have another question related to the similar situation, that is how to pick the first comparison. Yeah, so here, yeah, let me write that experience because we want to do summary a little bit. Okay, all right. The first comparison. So this summary is about the first comparison. Because first comparison, very important. In some of the questions, very important. Yeah. Some of the questions doesn't matter. Okay. Yeah. All right. So the first comparison here, you can see our current situation. All right. Current situation. X, 1, 2, 3. These three elements all have known information, right? So these three elements have known information. Okay? Then the remaining two elements, x4, x5, completely unknown, right? So we do not have any information about x4 and x5. Yeah. So that's the starting point, the situation. Yeah. Now you can see when we do first comparison, yeah, based on our results, we favor unknown elements, the first comparison. Favor unknown elements. Okay, see? So x4, x5, both unknown, we compare them. Yeah. Let me explain why when we apply our first comparison on unknown elements, you can get a maximum amount of information. More information you can get. Yeah. Later we have another important question. Question number 24. We need to use this idea. When you determine your first comparison, you need to do it on unknown elements. You can get a maximum amount of information. If in your first comparison, if there is a known elements involved, because known elements, that element is restricted, right? Yeah, it is restricted. So the information you get is impacted by that restricted element. Yeah. The flexibility is restricted by that one. So then you cannot get a maximum amount of information. Yeah. This idea we will see better in the question, in our question number 24. You will see. If you do your first part question with one known element involved, you get less information. Yeah. So, yeah. All right. So this is our experience. We get it here. Yeah. All right. And next one. Yeah. Number 14. Yeah. Most of you did fine. Yeah. So now. I feel not much, because most students can see, yeah. So this semester I didn't see any problem. Yeah, but the previous few semesters I see many problems. The problem is when we need to find 4 elements, not maximum, minimum, but we do not work on these 4 elements directly. We work on it indirectly. Okay? Indirectly. Yeah. So that is, we work on the complementary set. Okay? We work on the complementary set. On the set. Yeah? Yeah. So that is, we select max and min first, right? Yeah. We know how to do it. After that, remaining. Yeah? So remaining. Remaining 4 elements. That's our solution. Yeah. So this way. Yeah. This semester, I haven't seen any student use the direct way. Yeah. Because if you use direct way, try to find those 4 elements, not maximum. You need to do a lot of work. Too much work. Okay? Yeah. Yeah. But when you work on this, max and min directly, yeah, that we can do the minimum amount of work. Yeah. 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 Because I haven't finished the grading, so after I finish grading, I can see if there are some students, work on the 4 elements directly. Yeah. All right. Number 15. Yeah. So number 15. Yeah. So this question, actually, although most of you got the correct answers, but those students may not know the idea. So there are some very good problem-solving thinking in this question. Yeah. So I hope you can learn from this. Yeah. But some students just, do the formula. Okay. Yeah. Get the right answer. Yeah. But they may not know why we need to use the formula in this way. Yeah. So let me explain the main ideas here. All right. I still draw a diagram, so we try to understand the idea from this diagram. All right. So this number actually not that important. Yeah. Just big enough. Okay. Yeah. If the number big enough, so that specific number not that important in this question. All right. So now we imagine all these elements, they have some positions, right? So if they are sorted in the array, there are appropriate positions for these elements. All right. Then, what we're interested in, the top 12 elements. So we want to find one of the element in this top 12 portion. Okay? Yeah? So top 12, then the bottom part. Yeah. So we also need to know the bottom part. So we need to do subtraction minus 12. So we get 575. Okay? So there are 575 elements in the bottom part. Okay? All right. Now, we need to find one element that is not in that bottom portion. Okay? We're done, right? So that's simple. So from this diagram, we only need to find one element above this bottom 575 elements. That's all we need to do. Okay? Yeah? All right. Yeah. So that's our visual understanding. Initial visual understanding. We need to find some elements above this, bottom portion. All right. So next questions. How to use the minimum number of comparisons to determine one element that is greater than at least 575 elements. Okay? Yeah. So now we based on this understanding, we change our goal a little bit. Yeah. So we make our goal more specific. So now our new goal becomes find one element. Just one. Is greater than 575 elements. Okay, yeah. That's the new goal. That means, so we need one element that beats 575 elements. That understanding. In other words, this element only needs to beat 575 elements, not the maximum. So definitely, we don't need to find the maximum, right? Because the maximum elements will beat 586 elements, right? Maximum beats more elements. Here, we need to find an element weaker than the maximum. It only needs to beat 575. That means we need to do less comparison work than finding the maximum. Finding maximum, we know the solution, right? 586 comparisons. So we should use fewer number of comparisons to find this element. All right. Next, how to make this happen. How to make this happen. All right. Yeah. That's easy. So select arbitrary 576 elements. How about that? And find in these 576, because that's a subset, right? It's a subset of the original set. So find the local maximum with 575 comparisons. So we have that formula, right? So this n minus 1, right? Yeah. Comparisons. Yeah. Local maximum. It's not a global maximum. In this subset, we find a maximum. Okay? Yeah. Or partial maximum. Okay? Not a full maximum. Partial. Right? Then this local maximum beats 575 elements. Beats, right, because each comparison eliminates one element, right? So one element lower than this one. Now, we know, so that local maximum should be above the lower portion of that 575 elements, right? Yeah, so this is the local max here. That's a solution. Yeah. So using this way to understand why we apply that formula, right? Why we use the formula the total number elements, 587 minus 12. Yeah? So I saw most students just apply the formula, 587 minus 12. Gave the right answer, but why is correct? So those students, some of those students may not know why it's correct. So here, that's the reasoning. Yeah. So if you have this understanding, because later, with a similar context, we will have more questions. In our homework assignment number 2 and the final exam, we will have more similar questions, but I will add more conditions. In the future questions, not just so we need to find some element not in certain top portion and also not in certain bottom portion, right? Yeah. You know. That situation. Then you use this diagram to understand. Yeah. All right. Yeah. So that's this question. Oh, number 16. Yeah, number 16 also a lot of problems. Yeah. So let me explain. Number 16. Answer is 3. 3 comparisons. Yeah. But quite some students gave me 2 comparisons. Yeah. We need to do it for the worst case, right? For the worst case. Yeah. But those students who gave 2 may not be the worst case. Yeah. So let me explain why it's not the worst case. 2. Okay. All right. 9-element array. Yeah. We want to use the minimum number, that is, neither the maximum nor minimum. Yeah. All right. First, how important is this number 9 here? Total number of elements, number 9 here. Yeah. Many times, that specific number is not important. Yeah. So just like our previous 587, why that number is very important, right? Yeah. So for any number in that position, we can solve the problem. Okay? Yeah. All right. So here, this 9 element, we'll try to understand how important it is. Yeah. All right. So let me draw 9 dots on the line. Okay, yeah. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, all right. That's the whole set. Okay, that's the whole set with 9 points. Now, we work on this number of elements. So, remember, yeah, so here I want to, yeah, because I emphasize problem solving thinking. Yeah, because you need to have good understanding, yeah, not just to find the correct answer. You really need to learn how to think, how to do logical reasoning to solve the problem. Yeah, here. We need to do that. All right. Remember, one strategy I mentioned in our last class, or one of the previous classes I mentioned, we can modify the problem, right, to make it easier. Remember? Yeah. So when we have some relatively hard question, yeah, if we work on this question directly a little hard, then one way commonly used method, we modify this question slightly, make it easier, and solve this easier version first. After that, then we go back to the original question. All right. So this idea is very useful in many of our problem-solving questions. So we need to use this idea. Here, we need to use this idea. Yeah. So this idea, some other people give a name of this idea, called the golden rule. Golden rule of problem solving. You know how important it is. Yeah. So some people refer it to golden rule. So what's that golden rule? Oh, sorry. The meaning is, modify the problem to make it easier to solve. Yeah, so that meaning. All right, here, modify it. All right, how to modify it? Because then 9, we change the 9, yeah, because 9 is the size. We know when the size of the problem becomes smaller, the problem should be easier to solve, right? When the size of the problem smaller, then the solution tends to be, right? Solution tends to be easier. Now, we use this understanding. Can we choose a subset of this is our original set. Now, make the problem size smaller. How about we choose certain subset? The subset contains fewer number of elements, right? Now we work on the same problem on this subset and see what would happen. Suppose, yeah, because subset should be easier than the original problem, right? Size smaller, yeah, should be easier than the original problem. Think about it. If we can find a solution in this subset, what's that? So that means there is some element. Yeah, element. Yeah, let's say x0. Yeah, some x0. Not local max, right? Yeah, because the subset, its maximum minimum can only be local max, not a local minimum, right? Yeah. So this x0, we can find a solution. The solution, let's say x0. It's not a local max, not a local minimum. Can we say this x0 is also a solution of the original set, whole set? So can we say this x0 is also a solution of this whole set? So that means x0 is not global maximum. And it's also not global minimum. Yes, right? Yeah. Because x not a local max, that means x is smaller than local max, right? Smaller than local max. Different from local minimum, that means greater than local minimum. We know local max is less than or equal to global max, right? Local min greater or equal to the global min, right? So x0 must be between global max and the global min, right? So also a solution. See? You can see, when we change the problem size, we work on a subset. If we can find a solution, that solution can be used as a solution of the original set. Yeah. This idea. All right. If you understand this idea, now we have freedom to choose the subset, right? Yeah? When we have freedom to choose the size of the subset, what is the best case scenario for the subset? So we want to choose the minimum number of elements in the subset, right? Yeah. Minimum number, yeah? Because the smaller the size, the better for us, right? Yeah. So the minimum is we only choose the subset contains the 3 elements. Three elements subset. How about that? Yeah? So the easiest case we want to work, we select a 3-element subset to work on it. Yeah. 3-element subset, yeah? So let's select x1, x2, x3. Okay? Yeah. So we work on the smallest subset, x1, x2, x3. Yeah. Yeah. If some students ask me why smallest 3 element, because you need one local minimum, right? One local maximum. Then you need a solution. So you need at least 3 elements, right? Yeah. Because your solution should be different from local max, local min. Then you have at least 3 elements. So that's why the smallest problem size is 3. Now, this time you work on a much simpler problem. You have 3 elements. You need to find one that is different from the largest of the 3 and the smallest of the 3. What's that? Right? Yeah. It's the median, right? Yeah. Because the median, the one in the middle, right? Not the largest, not the smallest. So what you need to do is you need to find the median. Median of 3 elements. Yeah. Yeah. Median of 3. How many comparisons do we need? Median of 3 elements. 3 comparisons, right? For the worst case. Not 2, yeah. Some students, sometimes they give me 2 comparisons, find median, but that's best case. That's not the worst case. Median, you need to work on the worst case. So basically, you need to sort these 3 elements to get a median. Yeah. So in that case, so your final answer, 3 comparisons. Yeah. Here, so using this kind of thinking, golden rule, okay? Yeah, so later we will call it the golden rule. So you modify the original question to a simpler version. So we get the simplest version. And we know if we can solve the simplest version, that same solution, we can use it as the solution to the original problem. We don't need to change original problem. See? Yeah. So that's this question. Yeah. No, sorry. Yeah, I go a little slow. I need to control the time a little bit. Yeah, because I want to cover several questions that are relatively hard. Right? Yeah. Oh, number 17. I found a big problem. Yeah. So that's pretty common. So many students miss that. Yeah. Because those students just did half of the question. So they apply, we know this formula, right? Yeah. This formula count the maximum number of inversions without any condition, right? So here there is a condition. X11 is not in place. All right. So this one give us plug in 21, so we get 210. Yeah. Yeah. Several students just give this number as the final answer. You need one more step. Why? So when you get this one, you need to know what kind of input corresponds to this answer. What kind of input results in the maximum number of inversion? You need to know this information. Okay? Yeah. So the input results in the maximum number of inversion. That's this array in descending order. Descending order. That's the situation corresponds to the maximum number of inversions. Descending order. Okay? Any two elements gives you one inversion. Maximum number. All right. Now, descending order, then you need to look at the position of X11 in this descending order. Because X11 is the one in the middle, right? Yeah. Why you do the descending? Because we have total 21 elements. So X11 sits right in the middle when we have a descending order. Okay? Yeah. Input. Right in the middle, that means it is in place, right? Yeah. Yeah. It is in place. Yeah. 11. The subscript of 11 is supposed to be at a position 11, right? The middle one. Yeah. Yeah. So in place. But the condition does not allow us to put X11 in the middle. So in order to take care of this condition, we need to swap this X11 out of the order, right? Yeah. So do one adjacent swap. Yeah. Must be adjacent swap. We cannot go too far. If you go farther than the adjacent element location, then you will change more inversion. You will get more inversions, right? So one adjacent swap, because it only causes one inversion reduction. If it's not adjacent, then you may get a two inversion reduction, right? More than one. So then it's not maximum. So now you control it, yeah, because your adjacent swap could be this side. Yeah. Two-sided adjacent inversion. All right. So your answer, you need to do one, after that one adjacent swap, you do one inversion reduction, right? So the correct answer is 209. 209. Yeah. One induction, one inversion reduction, sorry. Yeah. Yeah. So that's the idea. Okay? Yeah. So most students, skip the second because they didn't realize the input corresponds to the maximum number inversion is in the descending order. Then X11 sits right in the middle in descending order case in place. Yeah. So they didn't realize this fact. Then, so I saw one student, wrote comments there, told me, nothing to do with X11. X11 is all right. We do not need to do anything. Yeah, but I couldn't remember name. Yeah, but things like that. Okay, yeah, things like that. Yeah, yeah. All right. Yeah, yeah. So that's this question. Yeah, but I need to move a little faster because I want to cover. Number 18, number 19, just look at my solution. Yeah, actually, there are many different solutions. Yeah, I saw some students got a answer different from mine, but still also correct. Yeah, so several different ways. Yeah, yeah. But right. Yeah. So I want to save some time. Yeah, because in my solution, just you do the, repeated squaring or cubing. Yeah, sometimes you need to do cubing, some squaring. Yeah, but I saw one student only use the squaring technique, but in a smart way. Yeah, so you can also get a best solution. Yeah, in some smart way. Yeah, yeah. Yeah. So here, let me save time. Number 20, number 20, I noticed one problem. So one student, actually, most of you are doing fine, but one student, that problem, careless problem. Yeah, because here our condition, you look at the inequalities we have, I only give you 4 inequalities, right? So that student understood in this way, okay, ellipsis. Yeah. So all the way from beginning to end. Yeah. So then many more inequalities. Then the answer is different. Yeah, because you understand. But here I didn't put the ellipsis there, right? So do not change that. So here, no ellipsis. So you should not assume we have all the inequalities in the middle. Yeah, all the way. Yeah, several students did in that way. Yeah, yeah. The whole method looks fine, but only the data, this part, the data part, not right. Yeah, quite some students did that. All right. So then I want to compare, talk about this one and another one. Yeah, number 21, and this one. Closely related, and they use the same idea. Then, same idea. If you use in this question, you're fine. But if you use the similar idea in question number 21, suddenly you get something wrong. So let me explain why. Yeah. All right. First, let me explain the most popular idea used in your solutions. First, we apply our standard formula. Yeah. We ignore the given condition, right? Yeah. So, yeah. N equals 20. So 3 times 20 minus 2. Yeah. 30, 28. Yeah, so this step. First step. Then we need to add this condition back and modify this answer, initial answer. But when we add these 4 inequality information back, we can say they can save 4 comparisons, right? Save us 4 comparisons. Yeah, that's correct. Yeah, so correct. So the answer is 28 minus 4 equals 24. No problem. Yeah, this idea. Yes, we can save 4. 4 of the 28 comparison can be saved by the given condition. Then, some students use the similar idea in question number 21. Then not quite right. Let me explain why. Yeah. All right. Look at the inequality. x1 less than x2 less than x3. 3 element in inequality. Yeah. Different from our previous question. 3. Yeah. So each inequality, 3 elements. 3 elements. 3 elements. Then, so they make the, conclusion like this. They said, each 3 element ordered chain can help us reduce 3 comparisons. 3 comparisons. Yeah. So that's they're based on that. Because we need 3 comparisons to sort 3 element array, right? We need 3 comparisons to sort 3 element array. Then, so they make conclusion. So each 3 element ordered chain equivalent to equivalent to the work for 3 comparisons. Okay? So that understanding. Work for 3 comparisons. And this understanding incorrect. Let me explain why. Okay? So the information you get from this 3 element chain is slightly less than 3 comparison. 3 comparison, we can do a little more than this. Actually, we can do a little more than this. Slightly less, so not equivalent, okay? Slightly less than 3 comparisons. The information we can get from 3 comparisons is a little more than this chain inequality. Why? I can explain it like this. All right. Suppose I have 3 elements. I can get more information, a little more information than this 3 element ordered chain. Let me show you. Now I use 3 comparisons. I do tournament method on 4 elements. X1, X2, first comparison between X1 and X2. Yeah, let's say the winner is X1. Second comparison between X3, X4. The winner is second comparison, the winner is X3, suppose. The third comparison between X1, X3, third comparison. Let's say winner is X1, okay? Yeah. All right. That's the 3 comparison we can do. Now, let's look at how much information we can get from these 3 comparisons. All right. Order the chain, the highest X1, below X1 we know it is greater than X3, right? Then X4 below X3. And we also know X1 is higher than X2, right? Now you can see, other than 3 ordered chain, you have another branch information you can also get. So the information can get a little more than 3-element ordered chain. See? Not equivalent. Okay? Yeah. So the given inequality is not equivalent. Yeah. So that's it. So if you make equivalent to comparison, when you do subtraction, you subtract more than necessary comparisons. Actually, equivalent to slightly less than 3 comparisons. 2 point some number comparisons. If you want to talk about equivalence, okay? Yeah. Let's say 2.7, 2.8, okay? Then the amount of information you get slightly less than 3 comparisons. So that way, actually, you use that idea. It's very hard to estimate what is the appropriate number you can say, right? 2.7, 2.8, none of them is exact, right? How to get exact such number, equivalence number. So that way is not good. So you should change. You should use a different way. You should avoid that way. So you should avoid that equivalence approach when you have 3-element ordered chains. Yeah. Here, because the middle one can be eliminated immediately, right? Before you work on it, because all the middle elements cannot be the maximum minimum. So out of consideration, we apply our elimination methods. 4 elements gone. So you remove 24 elements, you remove 4 elements. After elimination, you get a 20-element array, then inequality is another 3-element ordered chain. So 2-element ordered chain, right? Then the same as our previous question. Then you can use the method. Yeah. That equivalence, here, x1 less than x2, that equivalence equivalent to 1 comparison. That's okay, right? Yeah. That's okay, but you need to think about it may not be any this kind of inequality equivalent to equivalent to 1 comparison. You need to also think about only those comparisons can be used in the optimal solution. Then you can use that equivalence. Yeah. So those corresponding comparisons can be used in the optimal solution. Yeah. They can be used in optimal solution because our optimal solution, we do the pairing, right? Yeah. So every 2 elements we pair 2 elements. Yeah. So then we do comparison. They can be used in the optimal solution. So that's why we can use that equivalence approach. If some of the comparison cannot be used in the optimal solution, then your equivalence way still not correct. Yeah. So you also need to think about if some of the inequalities may not be that useful. Yeah. Some of the inequalities does not help much. That could happen, right? Yeah. Does not help in the full scale. Yeah, could be partially help, but not in the full scale help. Yeah, that could happen. Then you cannot make it equivalent to 1 full comparison. Part of the comparison, not full comparison. Yeah. Yeah. So when you use that equivalence approach, you need to be very careful. Sometimes it's correct. Sometimes it's not correct. equivalence. Oh, yeah, so here I use too much time, so let me try to, oh yeah, this number 22, so there is some big problem, very common. Many students, all right, so here we can, so some students use the, capital A represent the part inside the first parenthesis, capital B inside second parenthesis, capital C. That's okay. Then you need to calculate a to the fourth, right? A to the fourth times B to the eighth and C to the sixth. Then they did one round square sharing. One round B to the. Then they just count the number of multiplication. You haven't complete all the square sharing because between A and B you can still do more square sharing, right? Sorry, two here. So between A and B you can still do more square sharing, right? So A times B squared, another round square sharing. So many students just did a partial square sharing. So then still you can improve your solution with a few more multiplications. So you need to do as much as you can square sharing. The more square sharing you can do, the fewer number of multiplications you need. So that's this question. All right. So then the remaining I only can talk about one question. All right. So let me talk about the last question. Because I do not have that much time. All right, the last question, the answer is 14 comparisons. All right. First, when we start, so we already have winners group, losers group. So all these winner, loser, 5 pairs, right? 5 pairs. All right. Then we know, in our algorithm, we know the winners group we can get a maximum, right? Losers group get a minimum. Maximum with 4 comparisons, minimum also 4 comparisons. All right. Here, actually, we need to this step. We need to also. After this one, so also those students know we need to find a second local max because it's not a global second max, right? So after that, we also need to get a second local minimum. All right. The first thing is the information we get from max can also be used for the second local max. So here, some students did okay, using the tournament method. Tournament, okay, x1, x2, so winner, x3, x4, winner, x5, no pair for x5. All right. So then x1, the last round. Worst case, here we need to consider worst case x1. X5, that it won't be the worst case. Yeah, because X5, yeah, suddenly beats the best one, right? Yeah. So here, how do you get? Because the winner, X1 is the final winner. The winner, we need to look at which winner has more direct losers. Direct loser. 3 direct losers. If you make X5 the final winner, then there is only 1 direct loser, right? More direct loser, then you need to do more work. Okay? All right. So then, for second local max, all these 3 direct losers are the candidates for second local max. So you need these 3 candidates. 3 candidates, you need 2 more comparisons. 2 more comparisons. Yeah. So then that means you find max and local min total 6. So this part, you need 6 comparisons. Similarly, this part, you need also 6 comparisons. But that local max is not global. Second local max, not global. Suppose you have second local max, then so suppose this is max. Okay, this is max. This is second local max. Okay, but this one, the loser under the max, also candidate for second, right? So you need another comparison between second local max and the loser of the max. The loser under that max. All right? So 1 more. Okay? Yeah. And the minimum also the loser, the winner above the minimum. Okay? So another one. So the final answer is 6 plus 6 plus 1 plus 1. So you get 14. That should be the final answer. Yeah. So other solutions, I just post solution file. Although, if I have more time, I can explain a little more. Yeah. But now, yeah. So I cannot. Yeah. Yeah. All right. Yeah. So, yeah. I said the starting time to assignments 7 o'clock. Yeah. But I haven't posted the PDF file for part B. So after you leave, I will post immediately. Yeah. PDF file. Yeah. Because I don't want you to see too early, right? After I upload the file, everybody can see. So I don't want you to see too early. Yeah. Now I can post. Yeah.